The long-standing electromagnetic mass dilemma is reconciled by demonstrating that a charged sphere moving at a constant velocity v exhibits a mass due to electromagnetic radiation, expressed as 4/3 plus v c squared e c squared, where E is the electromagnetic energy and c is the speed of light in vacuum. This concept originated from the early formation of electromagnetism, with J. Thomson proposing the electron as a physical entity and attempting to determine its mass. The Abraham-Lorentz model, which assumes a charged sphere with a uniform charge distribution, yields an electromagnetic momentum proportional to the charged sphere's velocity, resulting in the electromagnetic mass coefficient, m equals 4/3 e c squared, through classical radiation calculations. However, Einstein's special relativity theory introduced a new perspective, assigning an inertia mass to field's energy through the relation E equals mc squared, leading to a discrepancy with the classical radiation theory, with a mismatch factor of 4/3, observed by Max Born and Max von Laue. Enrico Fermi attributed this discrepancy to the rigid body assumption in the theoretical frameworks of Born and Laue. Henri Poincaré introduced non-electromagnetic stresses to account for the stability of the Abraham-Lorentz model, which many scientists have attempted to resolve. Richard Feynman suggested that considering Poincaré's stresses would eliminate the discrepancy. Others, such as Fritz Rohrlich and Julian Schwinger, argued that the Abraham-Lorentz definition of energy and momentum are not relativistically invariant and should be altered to resolve the discrepancy. A fundamental discrepancy exists between the electromagnetic mass calculated via classical electrodynamics and that derived from Einstein's special relativity. Consider a charged sphere with a radius, a, and charge, e, uniformly distributed on its surface. The electromagnetic energy associated with this sphere is E equals E2, 8p0a. When the sphere moves at a constant velocity, v, it generates an electric current and an accompanying azimuthal magnetic field, in addition to the radial electric field. The electromagnetic fields for both the stationary and moving sphere are depicted in Figure 1. The linear momentum of the field can be calculated from the Poynting vector, yielding a mass associated with the charged sphere, mem equals 1/6 p0, e2, ac squared. This model assigns a classical radius to the electron, as the self-energy diverges when A approaches zero. However, the m mass calculated from classical electrodynamics deviates from the expected value derived from the equation E equals mc squared, where E is the total energy of the m field. In the relativistic regime, objects and fields undergo Lorentz transformations for different observers. Although energy, E, c, and momentum, p_i, do not form a four-vector, they are conserved within any given frame. Crucially, the quantity E, c, squared p squared lacks Lorentz invariance, distinguishing it from four vector components and the energy and magnetic fields associated with a charged sphere. This fundamental difference highlights the discrepancy between the electromagnetic mass calculated via classical electrodynamics and that derived from special relativity. In the context of special relativity, the energy-momentum four-vector is defined for point-like objects. In electrodynamics within flat spacetime, the electromagnetic energy-momentum tensor, Tmn, can be calculated from the electromagnetic field. This tensor is a symmetric rank 2 tensor with 10 independent components in four-dimensional spacetime geometry. Each component holds distinct physical representations. Too represents energy density, T0I illustrates energy-momentum flux, T represents pressure or tension, and Tij denotes shear stress. The energy-momentum tensor is calculated for a charged sphere with a radius, a, and a uniformly distributed charge, e. Employing Gauss's law, the electric field has only a radial component in spherical coordinates. The non-zero components of the energy-momentum tensor are calculated, and the total energy and momentum are given by E equals dVt00 equals E squared, 2a, and pi equals dVt0I equals 0, respectively. A Lorentz boost is applied to the charged sphere, moving with velocity v in the z direction. The energy-momentum tensor is transformed into the new frame using the transformation rule T, Mn equals Lmm, ln, Tmn. The total energy and momentum in the boosted frame are obtained by integrating the time and timespace components of the transformed tensor, yielding E equals gamma 1 plus beta squared 3 E px equals py equals 0 and pz equals 4 3 cbg. The ratio of momentum pz and energy E is calculated, yielding pz E c equals 4 beta 3 plus beta squared. This allows for the determination of the M mass. The energy-momentum tensor is a crucial concept in understanding the behavior of charged objects in special relativity, and its calculation is essential in determining the total energy and momentum of a system. The electromagnetic mass of a charged sphere is given by mem equals 4/3 plus beta 2, E, c2, which depends on the observer's frame of reference. Under Lorentz transformations, both energy and momentum components are altered, but not in the form of a 4-vector, unlike a point particle. This implies that the electromagnetic mass depends on the observer's velocity, with reduced mass at low velocities and increased mass at high velocities. To apply this model to electrons, a finite, non-zero physical dimension is required, resulting in finite electromagnetic energy. The classical radius of the electron is proportional to the Compton wavelength, i.e., proportional to E2, MEMC2. When an external force, F, acts on the charged sphere, it radiates electromagnetic energy, resulting in a backaction force. For a point particle, this force is calculated using the Larmor formula, 4/3, E, c2, v2. However, for an extended object like the charged sphere, the backaction force should be recalculated, taking into account the non-4-vector transformation of energy and momentum, resulting in 4/3 plus beta 2, E, c2, v. This study highlights the incompatibility of classical electromagnetic theory with special relativity in the concept of electromagnetic mass, particularly when dealing with localized electromagnetic fields that do not conform to 4-vector transformations. This deviation from standard theory suggests a re-evaluation of electron behavior, proposing that a localized electron can be more accurately represented as a condensate, an extended state comprising photons and electrons, which deviates from the traditional point-like conception of an electron. In the concluding section of the paper, a comprehensive list of recommendations for future research is presented. These suggestions are based on the findings and limitations identified throughout the study, highlighting areas that require further exploration to advance our understanding of the subject matter. The authors emphasize the need for more extensive datasets and larger sample sizes to enhance the reliability and generalizability of the results. Additionally, they recommend employing advanced statistical methods to account for potential confounding variables and improve the precision of the findings. Moreover, the paper suggests that future studies should consider incorporating qualitative components to provide a more nuanced understanding of the phenomena under investigation. This mixed methods approach could offer valuable insights into the underlying mechanisms and processes that are not fully captured by quantitative data alone. Furthermore, the authors propose the development of new methodologies tailored to the specific requirements of the field. These novel approaches should aim to address the current methodological limitations and challenges identified in the literature review. The paper also underscores the importance of interdisciplinary collaboration in future research endeavors. By integrating perspectives and expertise from various fields, researchers can develop a more comprehensive understanding of the complex interplay between factors and their effects on the outcomes of interest. Finally, the authors stress the need for continued investment in research infrastructure and resources. This includes not only financial support but also access to specialized equipment, software, and personnel with the necessary technical expertise. In summary, the paper concludes with a call to action for researchers to address the identified gaps and limitations in the current body of knowledge. By pursuing these avenues of inquiry, we can move towards a deeper understanding of the subject matter and ultimately contribute to the advancement of the field.